Hi, welcome back. This is the sixth lecture on topology and second lecture on continuity of match between two topological spaces. We looked at some examples. We proved one part of the mantra, right? A function between topological spaces is continuous. Okay, if it is continuous, then the inverse image of an open set in the codomain is open in the domain. Now we have to prove the converse. Okay, and then we will continue our journey with a few more examples. Okay, I hope everything is working fine. Right, okay. So this is a theorem which we wanted to prove. Let me just try again the option print out a pencil cursor. It's better as yeah. So this is a theorem we proved. We wanted to prove. Let x tau x, y tau y. These are topological spaces. If is a function, then is continuous if and only if for every open set V in tau of y, f inverse of V is open in x. So we proved one way. Okay, f continuous implies the condition. This is done. So let us assume, therefore what is our assumption now? We are assuming f is a function from x to y. I will suppress tau x and tau y, the topology, right? And with what property? If v is in tau of y, then f inverse of v is in open in x. Okay, then what are we supposed to prove? I have to prove f is continuous on x. Okay, so when do we say f is continuous on x? Yeah, okay, fix a, an arbitrary a in x, then I have to prove f is continuous at a, right? Okay, so let us prove that. So what do I know? So to prove f is continuous at a, what am I supposed to be given? This is my y, and so I am given an open set containing fa, call this v. Then what am I supposed to do? I am supposed to find a and an open set u containing a, so that for every x in u, fx should lie here. Right? This is what I am supposed to do. That is to find u like this. Yeah? But that is very easy. First notice that if I define f inverse of v, and I know this is open, this is given by hypothesis, by our assumption, right? Okay. Now do you see that a has to be in u? Why? When is a is in u? A is in u, that is f inverse of v. If and only if, let's go back to the definition, if and only if f of a belongs to v. But that is given, right? Because f of a is null. Therefore, a is in u and u is an open set. Right? Now let x belong to u. That means if x belongs to f inverse of a, that means fx belongs to v. Yeah? So what do you think I have proved? I have found an open set u containing a, so that for all x in u, fx belongs to v. That means f is continuous at a. But since I chose a arbitrarily, okay, this implies f is continuous on all of x. Do you understand the proof? Pause, review, proceed. Right? So now we have mantra in our hand. Okay, now we can do miracles, right? So what is that? Let's go back to the earlier question, right? Okay, let us go back. to the earlier question. What we said was, suppose I have identity map from x tau 1 or tau 2 to x tau 1, okay, where tau 1 and tau 2 are topologies. If I assume this is continuous, okay, right, assume let this be continuous, right, then what do I know? I know that if V belong to tau 1, then identity inverse of V belong to tau 2. But what is identity? When does an element x belong to identity inverse of V? That is if only identity of x belong to V. But what is identity of x? That is x. That is if only x belong to V. Right? That means, therefore, what do you think I have found? I have found that ID inverse of V is nothing other than V. Okay, we conclude this. Right? So, since I assumed identity is continuous and V is open in tau 1 and identity inverse of V must be open in tau 2, but then identity inverse of V is V. Therefore, V is open in tau 2. Therefore, what I have shown, if V belong to tau 1, I proved V belong to tau 2. That means tau 2 is finer than tau 1. Notice that tau 2 is the topology on the domain. Usually teachers will write x tau 1 to x tau 2. Since I always think of 2 is bigger than 1, so I wanted to think of tau 2 bigger than tau 1. So that's the reason. I hope you understand why I chose like that, because I don't get confused. Okay, I hope you also don't get confused. Okay, is that clear? So this we already proved. Now we are using mantra, we get a quicker proof. Okay, but actually the mantra used our arguments earlier. Okay, to show that if f is continuous, then f inverse v is open for every open set v in y. We used the argument which was seen when we tried to prove the identity from x tau 2 to x tau 1. Okay, please always go back. Don't get confused, because many students want very linear thinking. Okay, always go back and go through the earlier proof. Okay, then you will understand better. Right? Is the converse true? Right? In fact, I want to say it is if and only if. Continuous, okay? Is continuous if and only if tau 2 is finer than tau 1. Yeah? Right. That's also clear. Why? If V belong to tau 1 and tau 2 is finer than tau 1, right? Then identity inverse of V is V, and since V is in tau 1, we also belong to tau 2. Therefore, it follows. Do you follow? Did I go fast? Right? So assume, okay, tau 2 is contained in tau 1. Then I want to prove identity from x tau 2 to x tau 1 is continuous. To prove continuity, what should I do? Using mantra, start with a V in tau 1, I have to prove identity inverse of V is in tau 2 in the codomain, in the domain, right? But identity inverse of V, therefore I have to prove V is in tau 2. But what is our assumption? Tau 2 is finer than tau 1. That means every element of tau 1 is an element of tau 2. That's it. Okay? Pause, review, proceed. Yeah? So this leads to another observation. This is an easy observation. Suppose I have a function here from x tau x, okay, y tau y continuous, right? Then let's assume tau, okay, tau 1 is a topology on x and it's finer than tau x, right? Tau 1 is a topology, this is a topology where on x, and I am assuming it's finer than tau 1, right? Then I claim the function x tau 1 to y tau y is continuous. Remember again, to define the map, yeah, I don't need any extra structure, I just need only the set theory. Therefore, if f is a map from x to y, you understand? Therefore, F will turn out to be still a map from X to Y, except now X has a different topology. Right? Now I want to know whether this is true. I hope this is very easy, right? Again, let's use mantra. Let B belong to tau Y. Then what do I know? F inverse of B. Okay. F inverse of B, I know it is in tau X because F is continuous. F from X tau X to tau Y is continuous. Therefore, B belong to tau Y. What do I know? F inverse of B belong to tau X. Do I know that? Yes. But what is my assumption about tau 1 and tau 2? Sorry, tau 1 and tau X. This is contained in tau 1. That means whenever B belong to tau Y, this implies B belong to tau 1. Sorry, F inverse of B belong to the topology. That means F from X tau 1 to Y tau Y is continuous. I am giving lots of such abstract examples so that you get used to how to work with topology. Okay, quickly defining the continuity and then going to composition of continuous functions, etc., etc. They are all very easy, but these are the things which you will need in a professional thing. Okay, dealings. Okay, you may have to compare with various different topologies and learn to work with them. So this will be good idea. So what do we know? F from X tau X to Y tau Y continuous, and tau 1 is finer than tau X implies F from X tau 1 to Y tau Y continuous. This is the observation we made. Okay, then there is a dual observation. I will call it the dual observation. Don't worry about it if you don't understand such English words. What should it be? Can you guess? If you have understood my first lecture where I dealt with the discrete and discrete topologies and functions from discrete topology to any topology, or function from any space to indiscrete topology, okay, you should know what I am going to ask. Yeah, so the same thing. Let us assume X tau X to Y tau Y is continuous, right? Now let me assume tau 2 is a topology on Y so that tau 2 is coarser than tau Y, that is tau Y is finer than tau X. Do you understand? Then again I have a function from this space X tau X to Y tau 2, because F is a function from the set X to the set Y. Now they have different topologies, at least the codomain has a different topology. Now I want to know whether this is continuous. Is this continuous? That's the question. Is the answer clear? Start with the V in tau 2. Now what do I know about tau 2? Tau 2 is coarser than tau Y. That means any V in tau 2 is, okay, this implies V is also in tau X. Sorry, tau Y. This is tau 2. I'm sorry. Yeah, tau Y. Yeah? You are not confused, right? Okay. Right? Now what do I know? It is given to me X tau X to Y tau Y is continuous. This is given. This is my hypothesis. And V is in tau 2, therefore V is also in tau Y. And this is continuous, therefore what do I know? F inverse of V is open in tau X. Do you follow that? So what did I start with? You give me an open set in the tau 2 topology, right? I had to prove F inverse of V is open in X. That is, it must be an element of tau X. Now since V is in tau 2 and tau Y is finer than tau 2, V must be in tau Y. But my hypothesis says F from X to tau X to Y to tau Y is continuous. Since V is in tau 2, V is also in tau Y. Since F is continuous, F inverse of V must be in tau X. So I proved it. Yeah? Okay. So pause. Okay. Pause, review, proceed. Okay. Now let's look at some concrete examples. Yeah? Right. Therefore, suppose I have R with a co-countable topology and R with a co-finite topology, and the map is identity map. Do you think it's continuous? Why? Because call this as this. If U is in co-finite topology, that means U complement, that is R minus U, is finite. Therefore, U is actually countable also. That means U belongs to tau CC. You understand that? That means we had already seen tau CF and tau CC. This is finer than this. Therefore, the identity map is continuous. Yeah? And a more important example is R with tau L, the lower limit topology, with R with usual topology. This again identity map. And we had already seen tau L is finer than tau U. Therefore, this map is continuous. These are the applications. Okay? Make sure you follow. Do not be in a hurry. Right? Okay. Now let's look at one of our favorite examples. This may be the 6th or 7th example. Okay. Let's look at R with VIP topology and R with outcast topology. Do you remember? Whenever I deal with R, VIP is 0, outcast is also 0. Right? I hope all of you remember the definition of outcast and thing. So when does U is in tau V? If only 0 belongs to U. No, barring the extreme cases, empty set and R. And similarly, when does U belong to tau O? If only 0 is not in V. Again, let's go to the extreme cases. Okay? I am just quickly recalling the definition. Okay, now let's look at the identity map. I want to know that this is continuous. Yeah? Notice that this is no problem at all. Okay? Because what we looked at earlier was, you may say this follows from the earlier case. What was the earlier case? The earlier case said, let me see. Yeah, this is the earlier case. It said the following: the identity map between this, okay, if and only if the domain topology is finer than the codomain topology. Alright. So you may think, so if I prove none of the topology, this VIP topology is not finer than outcast topology, I am through. Do you follow that? Yes or no? Please pay attention. Yeah. So the question is here: tau V finer than tau outcast topology. What does that mean? That means give me any open set. For example, let us take one singleton 1. That is open outcast topology. Is it open here? Okay, this is in tau 0. But is a singleton 1 and tau V? No, because if it is non-empty set, if it is open, then 0 must be there. You follow that? Yeah? Therefore, we know this is not continuous. But there is a problem. See, for example, if I look at a function like from R to R, something like 0 here, and that is minus infinity to 0, it is 0. And 0 to infinity, it is 1, including 0. Right? Now the function is not continuous. This function f from R to R is not continuous in R, but then the real problem is only at 0. You understand that? At all other points, this is continuous, and here also it is continuous. Only at 0 it is not continuous. See, learn to think critically. Right? So, what is the question I can ask then? Okay, the identity map may not be continuous in all of R with the VIP topology. Maybe it is continuous at some point. Some points it may be continuous, right? Do you understand the question? Yeah. So we want to know this. Okay. So what is the question I want? Is identity from R with VIP topology with R with outcast topology continuous at some point. It may not be continuous in all of R. Okay, that's not. We already proved it. Maybe it's continuous at some point. Right? Do you understand that? So let A be such a point. Let A be not. Maybe F is continuous. Assume that F is continuous. Right? Now what is F of A? F of A is A. Right? Now what are the possibilities about A? So in VIP topology or outcast topology there are only one thing matters. What is that? Either whether I want to know whether A is 0 or A is not 0. Do you understand that? So suppose let us say A is 0. Maybe okay. Suppose A is 0. Can F? So we want to know whether F is continuous or 0. Now let us look at 0. Okay. F of A is 0. Therefore I have to find an open set B in tau 0 so that 0, that is A, belong to B. Now what is the only open set which contains 0 in the outcast topology? That is all of R. Now B must be all of R. Do you understand? Yeah? Right? Now what is the simplest topology, simplest open set in the codomain? Now I want to think of it as R as thing in the codomain. So here I can take U to be the simplest thing, maybe A. Please think. Okay, I don't need the, I can even take all of R, but always good to see the simplest one so that I can prove easily. Right? Now, what is F? Therefore, F of A actually belong to B. Therefore, what do you think I have shown? Do you understand? I have proved F is F from X with, R with tau V to R with tau outcast topology is continuous at A equal to 0. Right? We know it's not continuous on the full set of the domain, but at 0. Now let us see. Is it continuous at A not equal to 0? Let us see. Suppose A is not equal to 0. Yeah? I want to know whether it is continuous. Right? Okay. Let's look at. So, what is that I have to do? I have to look at F of A. What is F of A? A. Now, what I have to look for? I have to look for an open set in tau of O. Now, A is not equal to 0. Therefore, what is the simplest open set containing A in the outcast topology? Do you realize? I keep on repeating the same argument. Simplest or smallest or typical open set, etc. You see that how powerful that idea is? So naturally I can take A to be B to be singleton A. Right? Very good. Now what am I supposed to look at? I would suppose to look at an open set in tau VIP, and A should be there, and A is not equal to 0. Now what is the simplest open set which contains A in the VIP topology? That again you know, it is A and 0. This is a two element set. Since A is not equal to 0, this is a two element set. Right? Now what am I supposed to show? I am supposed to show, take any x here. I want to know whether fx belong to this. But fx is equal to x. Right? Now you have a problem. Right? If I take x equal to 0, right? What is fx? That is 0. 0, is it in A? No, because A is not 0. Do you understand this? Therefore, we have shown f is not continuous at any A not equal to 0. This f is again, I have to be careful, x is from R, VIP topology to R with outcast topology. This is not continuous at any non-zero point. How did you like this? Okay, now you will become very confident about continuity at a point, how to deal with and how to look for open sets. Okay, this is the beauty. The standard courses and books may not teach such things. Okay, so pause, review and proceed. Yeah, okay. So is there a counter question, a dual question you can ask? Of course you can again think of that, right? From R from tau O to R from tau V. That is from outcast topology to VIP topology. Case consider identity map. Okay, I leave it as an exercise. Okay, that's the only way you can learn mathematics. Okay, don't be hesitant. Please do that. Okay, what is the question? Exercise? Investigate. Points of continuity. Okay, not only continuity, points of continuity of identity map from where to where? R with outcast topology to R with VIP topology. Okay, first check whether it's continuous on the domain. Next you check at what points is continuous. Will you do that? Okay, I would like to hear the answer after you work out in the comment section. Please write down just to say that. What are the points of continuity, if any, etc. Right? Will you do that? Okay, let me assume that you do that. Okay, right. Now I want to go to, see, now what we did so far was we start with the topological space. Let me just change the thing. I start with x tau x and y tau y. I have map from x to y. Therefore, I can think of as a map from these topological spaces. I looked at continuity and points of continuity. Right? But most often to do analysis, to understand better, what we usually take is we take y equal to r and tau y equal to the usual topology on your. That then we say x tau x to r. This is real valued function. See, this is already a real valued function. Okay. Now I want to talk about continuity of real valued functions. What does that mean? Please understand. When I want to talk about continuity of real valued function, what do I mean by that? My codomain is R, but then I want to talk about continuity. Therefore, there should be a topology on R. What is the topology? It is always usual topology. In such cases, we will always write R. We will not write R with usual topology, R with metric topology, R with absolute value metric topology, nothing of that kind. This is standard practice. The moment I say it's a real valued continuous function, that means R is equipped with the standard usual topology given by the standard absolute value metric. Do you follow that? So we want, see, given a topological space x tau x, okay, we want to know, okay, the existence of continuous functions, real valued continuous function. Right? Of course, the answer is easy. Take f to be any constant. We know that it is always continuous. So the question is non-constant. Okay. In fact, sometimes we may even ask more. What we may ask, give me x and x2 in x, so that x1 is not equal to x2. I want a continuous function x tau x, real valued continuous function, so that fx1 is not equal to fx2. Then I say this continuous function separates these 2 points. Okay? Okay, let us think about it. Okay? Don't worry about that. Okay? First, in general, there may not exist. Okay? There may not exist non-constant real valued continuous functions on a given topological space. See, these are the things which topology teacher usually may not mention. Even when it comes to Reisman's lemma and Tier's extension theorem, he may not mention these things. Okay, right. So let us look at an example. So I am going to give an example. Suppose take R with co-countable topology. Right? You follow that? Okay. And suppose F is a continuous function, real valued continuous function. Right? Then I claim F is a constant. In fact, this example I found when I was an MSc student. Okay? Yeah, anyway. Why? So it's a constant. Suppose F is a constant, what do you think I have to prove? You will say that there is a real number, let us say y in R, so that for all x in R, fx equal to y, right? But in standard practice, if you had again looked at your real analysis, okay, when you want to prove your function, your differential function is a constant on an interval, okay, how will you prove that? Do you think that you will find a y? No. What you do, you fix a point and then show the value at any other point, that is, let me say that, okay, fix a point, call it x naught, take any other x, then you prove fx is always fx naught. That's it. Okay, you don't look, this is your y naught. You understand? Are you following me? That's why you will apply mean value theorem to get it in the case of a differential function, but that's an aside. Okay, because students are always afraid of real analysis. Anyway, now I want to prove it's a constant. So suppose now, okay, let me take an a which is not equal to 0, and let me assume so that fa is not equal to f of 0. If f is not a constant, then if f is assume f is not a constant. Okay, that means there exists a and r so that fa is not equal to f0. Right? If for every a fa equal to f0, then f is a constant. Do you understand? Right. And this a cannot be 0. Do you see why a cannot be 0? Because f is a function. Right? fa is not equal to f0. And if a is 0, then fa is not equal to f0. That means, okay, f takes two different values at the same point. Then it's not a function. Right? Very good. Always keep thinking. Don't give up. Okay. You have that. Right? Now let's look at. So I have f0. Okay. And see, I am writing fa as though it's less than f0, but it need not be. It could be even here. I don't care. Right? Now, do you see that I can find small intervals around this so that these are disjoint. That is, I can find an epsilon positive so that this is fa minus epsilon, fa plus epsilon, and this is f0 minus epsilon, this is f0 plus epsilon. These two intervals are disjoint. For them to make disjoint, what do I need? fa plus epsilon. If it is less than f0 minus epsilon, I am through. Right? Assuming fa is less than 0. f0. Right? Otherwise, it will be other way around. This will be f0 plus epsilon. This will be fa minus epsilon and fa plus epsilon. So I have to make sure this one. Are you following me? Okay. This means 2 epsilon should be less than f0 minus fa. Therefore, I can choose an epsilon so that f0 minus fa by 2 and epsilon is positive. Have you understood? Yeah? Therefore, what I have done? I have chosen epsilon so that these two intervals are boosted. Now there comes a problem. Now I am assuming f is continuous, right? F is continuous from R tau cc to R, right? Therefore, it's continuous at A as well as continuous at 0. So what does it mean? That means there is an open set tau cc so that for all x in UA, fx lies in the interval f of a minus epsilon to f of a plus epsilon, right? And similarly, there exists u0 in tau cc so that for all x in u0, f of x must lie in f of 0 minus epsilon to f of 0 plus epsilon. Yeah? Right? Now let us look at, you may recall when I defined co-countable topology, I showed any two non-empty open sets in tau CC intersect. Okay, there is always it's non-empty. That is intersection of any two non-empty open sets in tau CC is non-empty. That's very easy in case you have forgotten, because let us look at, suppose UA intersection U0 is empty. That means UA complement and union U0 complement must be all of R. But UA belong to tau CC, that means this is countable. And this is also countable. Therefore, the finite union countable set, this will be countable, therefore R is countable, a contradiction. Right? Therefore, what do I know? UA intersection UO is non-empty. But now I am in trouble. Now start with an x here. What happens? Then fx should lie in this interval. Yeah. Okay. F of a minus epsilon to f of a plus epsilon. Fx must be here. And fx, the same fx also should be here somewhere. But by my choice, these two intervals do not have any intersection. Their intersection is empty. Yeah? Did you prove that? Okay, can you prove that? These two intervals, fa minus epsilon, fa plus epsilon, intersection, f0 minus epsilon, f0 plus epsilon is empty. Why? Suppose there is an x is common here, let me call it alpha common here, right? What does that mean? That means alpha is less than fa plus epsilon. But alpha is here, that means alpha is greater than f0 minus epsilon. But f0 minus epsilon is greater than fa plus epsilon. Therefore, alpha is greater than fa plus epsilon, whereas alpha is less than fa plus epsilon. Do you understand? Am I going fast? Anyway, these are all very easy. If you have done my real analysis, okay, you will know all these things much faster. So, what I have found? Therefore, I have found out that this x has to be in fa minus epsilon, fa plus epsilon intersection, fa minus epsilon, fa plus epsilon, but this intersection is empty, a contradiction. So why did the contradiction arise? Because I assume there exists a real number a so that fa is not equal to f0. That means for every a in R, fa equal to f0. That means the only real valued continuous functions in R with co-countable topology is a constant. Only constant function. Do you see that? There are not enough continuous real valued functions on some topological spaces. Okay, please learn that. Even if you learn topology, you may not have seen this. I am sure about that. Yeah? Are you happy with this? You should be really happy, right? Okay, there should be a flash light. Good. Right. Now, the last example. This is the 10th example. Let us look at R with tau L, the lower limit topology. Let us look at any interval, any this this is an open set, right? In tau L, or for that matter any a comma b. This is tau L, right? Now let me define a function which is called the characteristic function, or sometimes the probabilist will call it integrator function of the set 0. Let me define a more general case. Suppose x is any set and a is a subset of x, then the integrator function, characteristic function, we usually denote by 1 integrator function of x. This is equal to 1 if x is in a and equal to 0 otherwise. Okay, therefore I am looking at the indicator function there. What is that indicator function? F equal to indicator function of the interval 0, 1. I claim I want to know whether it is continuous. So this is a real valued function. Do you see that? F is a real valued function from R with toggle to R, right? And I want to know that this is continuous. Okay. So what is that I have to do? Right? There are various ways of doing. Do you want to use mantra or do you want to check continuity at each and every point? Notice that if you draw the graph, it will be something very interesting. This is 0, this is 1. Therefore, here it is always 1. The graph will be here. And here it is always 0. Okay, let me just mark it differently. So this is 0. And here also it is 0. At 1 also it is 0. Do you understand? So with usual topology, you know this function is not continuous. Have you understood? So I want to know that it's continuous. So let me start with an open set B in R. Okay. So let us start with an interval. Okay. Let us start with an interval J, one open interval in R. Right? Because if you give me any open set U, it's a union of open intervals, right? Right? So let me prove for open interval. Are you happy or do you want? Okay, yeah. Right. Now there are two possibilities. Okay, my J, this is my 0, this is my 1, and my F takes only 0 or 1. Therefore, 0 and 1 may not be in J. 0 is not in J, 1 is also not in J, right? Then what is F inverse of J? It is empty set because X belongs to F inverse of J if only Fx belongs to J, but Fx takes either 0 or 1, but 0 or 1 is not in J. You understand? Right? Are you following? Now suppose only 1 belongs to J. Yeah? Then what will be F inverse of J? It is set of all X in R so that Fx equal to 1. But what is Fx? It is the indicator function. And when it is 1, if only X is in the interval 0 to 1. Do you understand that? This set is nothing other than 0 to 1. And this is in toggle. Right? Which is open. Have you understood? Yeah? And suppose 0 belongs to J. Then what is F inverse J? And 0 belongs to J and 1 is not in J. Right? And let me answer the same thing. I'm sorry. I should have said 1 is in J but 0 is not in J. Okay? And here 0 belongs to J. Then this set is nothing other than set of all X in R so that Fx is equal to 0. But because of indicator function, we know this is minus infinity to 0 union 1 to infinity. In our, when we define lower limit topology, we have seen this is an open set. Do you see that? I proved it. 0, 1 is open and its complement 0, 1 is also open. Do you remember? That is this set. Yeah? Therefore that's open. Therefore this is open. Now suppose 0 and 1 both belong to J. Then F inverse of J is R of R. That's also open. So what is that I have shown? So I have shown that for any open interval J, subset of R, F inverse of J is F tower. Okay. Now suppose you give me any open set V in R. Right? Then I know B is union of some J, okay, union of open intervals. Therefore, F inverse of B is union of F inverse of J, and these are all open and union of open set. Therefore, this is a towel. Now, notice that I quickly use something which I always said. What is that? Inverse images behave well with respect to set theoretic operation. That is, inverse image of the union equal to union of inverse images. Okay, please go back. As I said, look at my foundation lecture number 3, I guess, in which inverse images are done. Please review that. So what is the upshot? So what I have shown is the following. Okay, the indicator function of 0, 1, for that matter any interval from R tau L to R is continuous, but the same function 0, 1 from R to tau usual topology to R not continuous, right? Why is it interesting? That is, remember I already said that, see, tau L is smaller than tau U, right? So if I have a function f from R tau U to R, if it's continuous, naturally f from R tau L to R is continuous. Yes, because tau L has more open sets. So there may exist some function which is continuous from R tau L to R, but it may not be continuous as a function from R tau U to R. We have given one such example. Please rewind the video and go back and learn again. Okay, I hope all of you enjoyed. I have given a lot of very good concrete examples. If you go through these things, you will be 110% confident about continuity. Okay, it's not just a mantra and after that keep on doing various things. Yeah, and perhaps I will continue one more lecture with continuity to establish some more properties. Then we will return to set theory only, point set topology. Okay, there are various other notions I didn't introduce like closed sets, etc. I will do them later. Okay, I hope you enjoyed the lecture. Okay, please go through it at least twice. Okay. All the best. Take care. Stay safe.